Okay, hi everybody. Today I'll show you how to do problem number 27 from chapter 5. I can't show you the problem, but I'll read it out loud and you guys can follow along in your own textbook. So it says figure 5.27, which I have drawn over here, shows the speed of a person's body as he does a chin-up. Assume the motion is vertical and the mass of the person's body is 64 kilograms. Determine the force exerted by the chin-up bar on his body at A times 0, B times 0.5 seconds, C times 1.1 second, and D times 1.6 seconds. So, here I've drawn a free body diagram. There's this guy doing a chin-up on this bar. The force that the bar is exerting on the body is the normal force, which I've labeled N. Which is going upwards. His weight is going downwards, and his mass is 64 kilograms. And I define this way as the positive y direction. We actually don't need to worry about the x direction since he's only going vertically. So part A asks, what force does the bar exert on the body at 0.0 seconds? So at 0 seconds, we can use this formula. So the sum of the forces in the y direction, just that, is mass times acceleration. So the two forces that we're dealing with is normal and the weight. So we can change this formula up a little bit, substituting this in for weight. So what variables do we know already? We don't know the normal force since that's what we're looking for. The mass we know. G is the acceleration of gravity, which we know. Mass we know. We don't know the acceleration of the person at this point. And the way we find it is by looking at the chart that the question gives us. Or the graph, I mean. So I've drawn this graph exactly like in the textbook with the same increments and everything. And I've labeled some points. You don't need to use these points, but these are the ones I picked just for convenience. And if you look on the left side of the graph, you actually notice that it's a perfectly straight line. Same with the right side, but it's a straight line in the negative direction this time. The only part that actually curves is this upper part, but we'll deal with that later. So if you think about it in three parts, I labeled this positive straight line as M1. The very top is M2, and the right side of the graph with a negative slope as M3. So to find acceleration, we just need to find the slope of the graph at any given point. As we can see, this is a speed versus time graph. So we can say, that let's deal with M1 first, which is this increment right here, which is 0 to about 0.8 seconds. So we can say that between 0 seconds and 0.8 seconds, the acceleration is equal to the slope 1, which is, since it's a straight line, you can just use y2 minus y1 over x2 minus x1. We don't actually have to deal with limits, derivatives, and all that calculus stuff. So using the 2 points that I've chosen on this part of the graph, I'll say y2 minus y1 is equal to x2 minus x1. The units here is centimeters per second in the numerator and seconds in the denominator. So if we want to find acceleration as meters per second, we can multiply this by this conversion fraction, and that just gives us 0.30 meters per second squared as our acceleration in this time interval. So we can do the same for another time interval. Let's go with this one, the negative slope, so M3. This is approximately between 1.3 seconds and 1.7 seconds. So the acceleration during this time is equal to m3. And we're going to use the same thing as before, y2, and this time using these two these 2 points. So y2, which is 6, minus y1 over x2 minus x1. The units is the same. Multiplied by the conversion fraction like last time. Units cancel. We get negative 0.60 meters per second squared as our slope, as our acceleration during this time interval. And then we know at the very top of this graph, you can say that acceleration is equal to m2, and the slope at the top of a curve is 0, as I've drawn in by this dashed line. Yeah, so that's acceleration at the top, which is at 1.1 seconds. Okay, so now we found the acceleration for practically all points of the graph. Now going back to our original problem, we've gone this far so far. So let's just start substituting in numbers for these variables. And we get, or actually first, I'm going to move mg to this side. Factor out m just to make it a little cleaner. And now we're going to start substituting in variables. So we're going to, substituting in numbers. So the mass is 64 kilograms. The acceleration at time equals 0 seconds is what we've proven before, which is between 0 and 0.8 seconds. The acceleration is 0.3 meters per second squared. So we're going to start plugging that in. 0.3. Our g is the acceleration due to gravity. And when you simplify all of this, you would get 646 newtons, and it's going up. So that's your answer to part A. Part B asks, was the force of the bar against the person at time equals, 0.5 seconds. Using the formula, same formula as up there. Gonna move mg to the other side like before. Now, we're going to start substituting in numbers like before. 64 kilograms for the mass. The acceleration at 0.5 seconds. Let's look back at our previous work. We found that at 0.5 seconds, which is between this, it is still 0.30 meters per second. So that's acceleration we're going to plug in. 0.3 plus the g is the acceleration due to gravity. Meters per second squared. Simplify that and we get the same thing, since this is the same essentially the same problem as before. 646 newtons up. Now, moving on to part C, this time it asks for when time is equal to 1.1 seconds. Same formula. I'm just going to cut to it. Is equal to, never mind. I'm just going to go with this again. Move mg to the other side. Alright, so now we're going to start substituting in numbers again. So we're going to put in 64 kilograms for the mass. Acceleration this time at 1.1 seconds is, if we look back here, we see that at 1.1 seconds, which is the top of our graph, our acceleration is equal to our slope at that point, which is equal to 0 meters per second squared. So that's what we're going to plug in for part C. Oops, let's try. Now, acceleration, 0. Acceleration due to gravity, 9.8 meters per second squared. Simplify that, and we get 272 newtons up. Now, last part of the question, part D. What is the force at time equals 1.6 seconds? Using the same formula, now start substituting in numbers. Mass is equal to 64 kilograms. Now in this time, the acceleration, we're going to look for when it's at 1.6 seconds. And we see that 1.6 seconds falls within this time interval. And we're going to find that the acceleration at this time interval is negative 0.60 meters per second squared. So now we're going to plug that in for our acceleration. Oops, yeah, I'll slide it up a little bit. And our 9.8 meters per second squared. Simplify that, and you get 589 newtons up. So those are your 4 answers to this problem. I hope this video was helpful, and yeah.